Okay, so we're going to have a look at reflectional symmetry properties of quadrilaterals. So there's lots of different examples you can explore. For example, a square has 4 lines of symmetry. And also, when you think of a rectangle, has 2 lines of symmetry. And so does a rhombus, a diamond shape like this. You've got examples with 4 with 2 lines of symmetry. You can also come up with examples of quadrilaterals that only have 1 line of symmetry. So for example, an isosceles trapezium, where these 2 sides are the same length. This has just the 1 line of symmetry, and so does a kite, whether it's convex or concave. And finally, you can also come up with lots of nice examples where your quadrilateral doesn't have any lines of symmetry, for example, a parallelogram, or just a strange one with no symmetry. So the question is now, can a quadrilateral have exactly 3 lines of symmetry? Can we come up with some sort of example? So do, if you're interested, pause the video, have a go, see if you can come up with an example with 3 lines of symmetry. And you may find that you're able to come up with some examples. For example, an equilateral triangle has 3 lines of symmetry. And you can draw a hexagon that's got 3 lines of symmetry as well. And it looks like this. And for a quadrilateral, maybe you've got something like this, where you've got 4 vertices here, 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 and here. And this does have 3 lines of symmetry, I suppose. But the problem with this is it's not really a quadrilateral. This is just one edge. It doesn't have a vertex here. This is a straight line. So this is actually just another equilateral triangle in disguise. So maybe it's not possible for a quadrilateral to have exactly 3 lines of symmetry. And if it's not, then we should be able to prove it. So let's try and prove that it's not possible for a quadrilateral to have exactly 3 lines of symmetry. So there's lots of different types of quadrilaterals, lots of different ways that they can have mirror symmetry. So in order to sort of cover all the different cases, we'll take an approach here of splitting up into lots of different cases. So just sort of to get us started, if you imagine obviously we're going to have at least 1 line of symmetry, the case we're interested in. We call this L. It should be clear that it's not possible for all 4 of your vertices, all 4 corners of your quadrilateral to lie on L, because otherwise it wouldn't be a proper quadrilateral. So this isn't allowed. So if we start now, we can write the beginning of our sort of rigorous argument here. So consider a line of symmetry, we'll call this L. So there must be at least 1 vertex, we'll call this A, which doesn't lie on L, because you can't have all 4 of them lying on L. And it's interesting as well, if you've got a vertex, say it's A over here, it's also going to have a reflection over on the other side, which we can call B. So there's actually going to be 2 vertices that don't lie on L, at least 2. So also A has a reflection, which we'll call B, in the line L. And let's label the other 2 vertices as C and D. Okay, so what we're going to do now is we're going to actually split up into some cases depending on the position of where C and D lie relative to A, B, and our line L here. So what we'll do is the first case, call this case 1. So this is where C and D both lie on the line L. And this is still actually covering quite a lot of different cases, so I'm going to split this up into 1A and 1B. So case 1A, I'm going to say, is where C and D, they both lie on the line L, but then they're actually both on the same side of this line joining A and B here. So C and D both lie on L on the same side of the line segment joining A and B. Okay, so just our kind of general picture then, case 1A, we've got our line of symmetry L, we've got A and B, and then we've also got C and D somewhere down here, or they could be both on the other side. Okay, so now how do we join these up to make a quadrilateral? Well, there's only actually one sort of real possibility that's going to work here. So what we could do is we could join them up like this and make a concave kite shape, which has, well, this only has one line of symmetry, so this certainly doesn't give us the 3 lines of symmetry we're looking for. And there's another option to join them up, say perhaps if you tried to join A and B with an edge, but at this point you would get kind of stuck, because then if you want to join it into a quadrilateral, you would end up breaking the symmetry here. You get some sort of another concave quadrilateral there, but this won't work either. So basically, case 1A, the only possibility is that you get a concave kite, which has one line of symmetry. So now we'll cover some of the other cases, so 1B, then we'll also have a look at case 2, and we'll perhaps have to split that up into 2 cases as well, and try and show that it's never going to be possible to have 3 lines of symmetry. Now, it's not actually possible for a vertex to lie on this line L and also intersect this line joining A and B. So I'll show you what I mean here. Imagine you've got A and B here. It's not possible to have another point that actually lies on this line between A and B, because then you wouldn't really have a proper quadrilateral. It would actually be a triangle. So this isn't allowed, which means that basically the only other possibility we need to consider in case 1, where C and D lie on L, is the case where they're on opposite sides of this line joining A and B. So let's draw out what this can look like. So you could get a kite shape, for example, where we join all of these up, and this has one line of symmetry, which is no good. It's not 3. You could also have a rhombus if some of your distances, so this distance along here is equal to this distance here, then you would have a rhombus, or a diamond shape. And this has 2 lines of symmetry. And also, if you imagine you squash these in a bit more, you can also get a square as a very special case of having a rhombus, which we know has 4 lines of symmetry. And these are the only possibilities here, where you've got your points C and D both lie on this line. So you can either have 1 line of symmetry, 2 lines of symmetry, or 4 again here. So actually it seems that for the whole of case 1, splitting into case 1A and 1B, there's no possibility where you have 3 lines of symmetry. So now let's consider case 2. Okay, so now we're actually done with case 1, where both of C and D lie on L, and we don't need to consider the case where only one of C and D lies on L and the other one doesn't, because then what would happen in that case is, imagine you've got your A and B here, and maybe C doesn't lie on L. Well, that would ensure that D, in order to be the mirror image of C, would not lie on L. So it's not possible to have just one of them lying on L and the other one not. So we just need to consider for our case 2 the case where C and D don't lie on this line of symmetry L. And the way we're going to consider this is actually by splitting this up into 2 different cases. So C and D don't lie on L, and I'm going to consider first for case 2A the scenario where C and D don't lie on L, and they form edges which are parallel to the line of symmetry L. So let me draw out what I mean here. Basically, you've got your line of symmetry L, you've got your A and B either side of it, and then perhaps you've got C is up here and D is down here, and they form edges which are parallel to your line of symmetry L. And this gives you a rectangle, or it could also possibly give you, if you've chosen them just right, it could also give you a square. So this can give you either 2 or 4 lines of symmetry, which is no good. So case 2a, you still can't get 3 lines of symmetry. So what about case 2b then, where they don't form edges parallel to L? So let's write this out. Case 2b, so this is, once again, C and D don't lie on the line of symmetry L, and don't form edges which are parallel to L. So you get some sort of picture kind of like this. Let's draw another one. You've got your A and B down here, and then maybe your C is here, so it's not forming an edge which is parallel to the line of symmetry L. And then your reflection D will just give you the same picture. Of course, C and D could be swapped around in this picture. This gives you 1 line of symmetry. This is an isosceles trapezium again. And you could also have, of course, where A and B are actually closer to the line of symmetry than C and D are, but once again, this is still giving you an isosceles trapezium with 1 line of symmetry. So you can only get 1 line of symmetry in this case, which is no good. So we've covered all of case 1 and all of case 2 by splitting this up into 2 different cases, and we've shown then that it's not possible to have exactly 3 lines of symmetry. So we can conclude, therefore, a quadrilateral cannot have exactly 3 lines of symmetry. This is a really nice sort of proof by exhaustion. We've covered all the different possible cases, shown that it's not possible to have 3 in any of those cases, and then we're done.